Okay, so it's a real pleasure to be here today to talk about a subject I'm very passionate about, supermassive black holes. I'm part of the faculty here in physics and astronomy. My research area is astronomy and astrophysics. And I'm going to actually immediately take a little detour away from supermassive black holes, but to share some other very exciting news. And that is that Ohio University is building an observatory. This is to be located at the Ridges. Construction is underway right now. It will be completed later this spring with the grand opening on May 6th. This will house a historic refractor telescope that has been out of commission for a number of years. It's actually been a long time since we had a functioning observatory on campus. So this is a very significant development. And so the function of this observatory is not really for research. It's for public outreach, stargazing, and our introductory astronomy classes. So after the grand opening, I know it's after classes are out, many of you will not be here. However, after that time, we will have a program of public events where you can come and look through the telescopes and we can talk about what you're looking at. And you can also enroll in one of our introductory astronomy classes, and we have one of our instructors of that, George Ebert's sitting right here. He can tell you all about the class. It's a real blast, and encourage you to consider doing that. Okay, if you have questions about the observatory, we can delve into that more later, but I'd like to go ahead and start talking about supermassive black holes. Okay, so to set the stage, I'm going to do a little historical narrative here about how this understanding has progressed through a series of discoveries to lead to this realization that these very exotic objects even exist. Okay, so if you go outside and you look at the sky, you use your eyes, which are sensitive to visible light, right? Light, to a physicist, light is a form of electromagnetic radiation. Visible light is only a part of the total spectrum of electromagnetic radiation. And our eyes are only sensitive to a certain range of wavelength or frequency. Our eyes interpret wavelength or frequency as color, right? So red light has a different wavelength or frequency than blue light. But there's a whole large part of the spectrum outside of the visible range where there's other kinds of light. So if you go to longer wavelengths, you go to the infrared part of the spectrum, right? If you go to shorter wavelengths, you go to the ultraviolet, and it keeps going. So at long wavelengths, radio waves are another form of electromagnetic radiation, right? It's another form of light. Our eyes can't see it, right? Same with X-rays. Okay, so in the history of astronomy, especially in the 20th century, there's a very important sequence of developments as we've gone beyond just looking at the sky in visible light and open up other parts of the electromagnetic spectrum to look out at space, okay? So the first part of the electromagnetic spectrum where this played out was in the radio range. So during the Second World War, there was a lot of investment in research around radar technology, which led to the development of very sensitive radio receivers. And so in the post-World War II era, this radio astronomy field really sort of took off. Okay, we started to map the sky, make measurements at radio wavelengths. So here's a radio telescope. Looks like a satellite dish because it's basically the same technology. It's a big radio telescope. It's not very far from here. Green Bank, West Virginia. Who's been to Green Bank, West Virginia? Okay, we've got a few people who've been there. There's an amazing observatory. It's not that far away. It's a 4-hour drive straight east from here. Beautiful. Not much around there, which is why the observatory is there. Close to Snowshoe Ski Resort, if that helps place it for you. Okay, so there's actually a much bigger, more modern telescope there now, but this one is visually interesting is why I put this here. But telescopes like this were used in this era to start looking at the sky. And what we quickly discovered is the sky viewed at radio wavelengths looks very different than what we see in visible light. Okay, so people started doing surveys, finding these bright radio sources in the sky. They wanted to understand them. So they would compare their radio map to a visible light map, right? Okay, so we start finding these bright radio sources. So one of the early surveys that was carried out at the Cambridge University Observatory, and this is their third survey, 3C, source number 48, 3C48, famous very bright radio source in the sky. Now, what you're seeing in this image is actually the kind of imagery we had at the time in visible light. It's a photographic image. It's a negative image, right? So stars, bright sources, are actually the dark things here, okay? So, so you see a field of stars, or things that look like stars, and somewhere in that field is this really bright radio source. The thing is, there's a whole bunch of stars. They all look basically the same. You know, a few are a little brighter than others. Where's this booming radio source, right? And why would it look different than the others, okay? So you think you know which one it is? The big one, right? Well, you might think, you know, the brighter one might be it, but in fact, it's not the big one. It's the one right here in the center, which looks pretty unremarkable, right? So why is that such a strong radio source? Well, after these were initially identified, what we call the optical counterpart, right, the visible light source, the next step to unraveling this mystery was to go out and take the visible light and do the equivalent of spreading it out to be a rainbow, right? Take the spectrum, because you can learn a great deal from looking at the spectrum of that light. Okay, so you take the light from that star, do the equivalent of passing it through a prism to make a little rainbow, right? And look what you see in that rainbow. So here's the spectrum of one of these sources. So what these came to be known as, they look like stars, and they're radio sources. So people call them quasi-stellar radio sources, or quasars for short. So what are these quasars? So people took spectra of these, and the first thing they noticed is these don't look like stars, okay? What's shown here is this is wavelength or color plotted on the horizontal axis, right? So blue are at this end and red at that end. And then this is the brightness at each wavelength or color, okay? So you can see there are certain colors where there's a huge amount of light, right? These spikes. And those are called spectral lines, okay? They have this vertical aspect. They look like lines in the spectrum. Normal stars don't have those, okay? So now we know a little bit about spectral lines. There are nebulae, different kinds of objects out there that have spectral lines. And spectral lines originate from changes in the energy state of atoms. Okay, atoms and whatever material is out there go from a higher energy state to a lower energy state, and they spit out a photon of light at a particular wavelength reflecting that energy state change. So these lines are like a fingerprint, right? They appear at certain wavelengths or colors, and you can say, I measured in the laboratory, that's a line of hydrogen or carbon or whatever, right? The problem is we see spectral lines in this quasar spectrum. We go compare it to what we measured in the lab, nothing matches up, okay? What's going on? Okay, how can this possibly be? And what was realized after time, in fact, you can identify this pattern of lines, but they're not where you expect them to be. They're shifted, okay? And the sense in which they're shifted is that this pattern of lines is a set of lines that should appear in the ultraviolet part of the spectrum, right? Way down here at shorter wavelengths. This is a carbon line at 1548 angstroms, or 155 nanometers, right? It's way out here at 8,000 angstroms. It's shifted to the wrong part of the spectrum, right? So we can identify the pattern, but it has this offset. Why is that? Well, in fact, we know why we get these shifts when we look at astronomical sources. It's called the redshift. And it arises from the expansion of the universe and the fact that objects that are further away from us are moving faster, and the whole spectrum gets shifted or stretched, actually, by the expansion of the universe, kind of like a Doppler shift, so that the features now appear at longer wavelengths. It's the redshift. Okay, now we know something about this, but the fact that it's so redshifted means that this is not a star, right? Stars are nearby things. This is a tremendously distant object. And for us to even see it means that it's very powerful, okay? And it has these strong spectral lines, it has this radio emission, and these are bizarre things. Okay, the next important step was, looks like a star, but is it really a star? A key part of our advancing our understanding of these was the launch of the Hubble Space Telescope in 1990. And I'll have more to say about Hubble later on in this talk. So Hubble has the ability to take images that allow us to see fine details in sources on the sky, right? That's one of its really excellent attributes. When you image these quasars, quasi-stellar radio sources, with the Hubble Space Telescope, you see, aha, there's this bright source, what looked like a point source, like a star. It's actually surrounded by additional emission, nebulosity. And in fact, we know what we're looking at. We are looking at galaxies, okay? So who knows about galaxies? Do you know about galaxies? What galaxy do we live in? The Milky Way, exactly. We live in a galaxy. A galaxy is a collection of stars and gas and dark matter held together by gravity, right? And we live in a galaxy. There's lots of galaxies out there, okay? And these are galaxies we're looking at, but these are not normal galaxies. They have this incredibly powerful source in their center that's pouring out radiation and radio emission and all other kinds of stuff, right? Something unusual is going on. This is illustrated even more strongly if we go back to looking at radio wavelengths, right? And we zoom in with a radio telescope on some of these quasars, and you see things like this. Okay, so this is if your eyes could see radio wavelengths, this is what you would see, right? So very bright compact source here, and then these fluffy things out here, and then this very skinny connector right here. What is that? What's going on here, right? Well, it turns out through a series of measurements, we know what's going on. This radio emission is being produced by ionized gas, a plasma, right, being shot out at a speed close to the speed of light, right, relativistic speeds, being shot out, and it piles up out here when it runs into some material in the surrounding environment, okay? You get the same thing on the other side. Why is there a jet on only one side? I mean, where's the jet that would be piling up here? It's there, but it turns out you can only see it on one side. Why can you only see it on one side? If you take this matter moving at close to the speed of light, if it's sitting still, it's radiating sort of equally in all directions. But once you speed it up to close to the speed of light, the radiation pattern changes due to special relativistic effects, and it gets beamed in the forward direction, like a searchlight, okay? So that means we see this one because the jet is coming towards us, right? It's angled a little bit, but this one's coming towards us, so we can see this cone of emission. This one's pointed away. That's why you can't see it. You know it's there because all the stuff's piling up out here. And you can actually do types of radio measurements that illustrate how fast this is moving. Okay. Tremendously powerful sources, bizarre jets of ionized gas shooting out at close to the speed of light. Yes?
What's that, like, really bright thing
The
there?
really bright thing in the center, that's where all the action is, okay? That's where all the action is, and it's something pretty weird, right? And we now think we know what that something pretty weird is. The picture that has emerged is that the thing that is powering this whole system is a black hole, okay? Black holes are black. How can they power a system? What you're seeing is the release of gravitational energy, okay? So we all know about gravity, right? If I take this ball and it's sitting still, right, and I turn it loose, and what happens? It speeds up, right? It accelerates until it hits the floor. So it's gaining what we call kinetic energy, energy of motion, and it's deriving that from gravitational energy, the pull and acceleration exerted by Earth, okay? So when you have a source of gravity, if you have matter falling towards that source, you can convert the gravitational energy to energy of motion. Kinetic energy, or if you have a gas, that kinetic energy can turn into thermal energy or heat. Okay, so if you have matter falling in towards a source of gravity, a gas, you can make it very hot. Well, so we're talking about black holes. I know a bunch of people here know about black holes, so What do you know about black holes? Why is a black hole black? Yes? Light cannot, the gravity is so strong that not even light can escape from it, right? And why is that? If you take a mass, some sort of matter, and you squeeze it to a smaller and smaller size, at its surface, the gravity is getting stronger and stronger and stronger, right? The reason being that if you're standing on the surface, the distance between you and the center of that mass is shrinking, and gravity gets stronger as the separation between masses gets smaller. Gravity gets stronger as the separation diminishes, okay? So black holes involve squeezing this matter down to this tiny size to the point where gravity is so strong, not even light can escape. So that means if you drop matter towards the black hole, it can get sped up very fast and generate a lot of heat, which comes out as this radiation, okay? So the engine, the power source of these quasars are black holes, and the source of energy is the release of gravitational energy as matter is on its way down towards the black hole. So we think in many cases that matter, as it collapses, sort of pancakes and it goes into an accretion disk, and the friction in that disk causes it to heat up as it spirals in, where you get all that light. Yes?
Why is the black hole so light? How can you see it and it's not like usually black?
How can you see the black hole when it's supposed to be black? Excellent question. The reason is this is still outside the zone where the light can't escape. Okay? There's a region, right, around where the light cannot escape, and we're outside that region so the light can escape. Okay? So if you go past that point of no return, you're never coming back out, right? So all this stuff you're seeing here is outside that Schwarzschild radius, right?
So why does the black hole spin?
Why does the black hole spin? We're not there to spin yet, but I'll tell you why. This matter is spiraling in, and it carries that spiraling motion into the black hole, so the black hole itself will be spinning, okay? Its angular momentum, is the physics word, is carried into the black hole, and the black hole preserves that. Okay, so that is probably related to these jets that come squirting out, and that is involved with, they're probably driven by magnetic fields in that material that's on its way down into the black hole. That gives rise to those jets we see with this plasma shooting out and producing the radio emission. Okay, so now black holes, the other piece to this is, remember, these are so powerful, you can see these out to huge redshifts, meaning huge distances. There's an enormous amount of energy being released. The amount of energy is related to the mass of the black hole, right? If you had just a wimpy little black hole, and you're pouring all this radiation out, the radiation itself will push away the surrounding matter and the whole system shuts off, right? To keep this going, gravity has to win and keep pulling in more matter. And for gravity to win, if you're blasting out all this radiation, you've got to have really strong gravity, which means you've got to have a really massive black hole. There's a straightforward way to calculate what the mass of those black holes is, and for the powers that we see coming out, the energy coming out of these quasars at large distance, the black hole has to be anywhere from 1 million to 1 billion times the mass of the sun. That's why we call them supermassive, okay? Okay, so pretty amazing. There's something else very important. We see these at large distance. It takes time for light to travel from a source out there in space to reach us, right? The light we see now was emitted sometime in the past. So analogy would be, you live in America in the 1700s, you've got a friend in England you're corresponding with, right? You're writing letters back and forth. So suppose you get a letter today. The way we communicate in the 1700s to England is by letters that go on sailing ships that take anywhere from 60 to 90 days to cross the ocean, right? The letter you're opening today is telling you what was going on over in England in November, okay? So you're getting this message, it's telling you about something that was going on in the past. It takes time for that communication to reach you. Here the communication is light emitted by the source out in space, and so when you receive it, it can be a long time from when it was emitted. In fact, these quasars are so far away that the light has been emitted in many cases billions of years in the past. Billions of years in the past. So the universe itself, we think, is about 13.7 billion years. You can see these quasars out to, 5, 8, even more billions of years. You can see this light emitted from a source when the universe was a much younger place. We are looking back in the past when you look at these sources out there in space. You're looking at the universe when it was younger. Okay, you tend to see these quasars only at large distance. So what does that mean? Think about that you carve out a cube in space and you let it expand with the expansion of the universe, and at different times you look at what's in that cube. And you do that in different locations, right? And so what you find is we see these quasars at redshift, at high redshift, at large distances when the universe was a younger place. And we sort of do an inventory of what's in that box, right? And then we look at a similar box nearby and we do an inventory of what's in there. And we see on average, there's lots of quasars when the box was out there, when the universe was younger. And we don't see them around us nearby, right? Use the expanded box now, what's called a co-moving volume that encompasses the expansion of the universe, and do the inventory, and something has happened to the quasars. That's why we don't see them nearby. We only see them at high redshift. So what has happened? Okay, so let's remember what it takes to produce a quasar, right? Supermassive black hole to give you very strong gravity. That's not enough. You've got to have this material going into it to get really hot and radiate. Aha, that's the fuel. You need black hole, you need fuel. So what we think has happened is the fuel source has tapered off between back then and now. Okay? So there must be less gas around the black hole to go in and radiate all this power. Okay, so, but fuel source is gone, what's left behind? Fuel's gone, there's two pieces to this. What's the other part? The supermassive black hole, right? They should still be there. Where are all those supermassive black holes that were powering the quasars? We know they were around back then. They should still be around somewhere today. Where are they? Okay? So this motivates people to go look where you might find these. So remember that the quasars live in galaxies. They live in galaxies, right? So the remnant black holes, the burned out quasars, probably are in galaxies. So good thing to do would be to go look in galaxies. So what would be the closest galaxy we might go looking for a black hole? Yes? Andromeda is a good bet. We'll come back to that, but there are closer options. What's a closer option? Yes? Our own Milky Way. We live in a galaxy, right? So, is there a supermassive black hole in the Milky Way? And the answer is, let's look in the center of the Milky Way, right? That we think these quasars are in the centers of galaxies. Here's if you look in the center of the Milky Way, and this is actually a technically challenging thing to do, but people have imaged the very center of the Milky Way, and you can see stars in the center of the Milky Way. And this is actually sort of a graphical representation of the pattern of stars that you can see. Okay, so I'm going to show this little movie that people from Caltech have produced, from UCLA. Sorry. Okay, so pay attention to what happens to these little dots. And you can see the year is shown up there in the top right. This has been observed for like 20 years. So what happens? First thing you notice is, are the stars sitting still? They're moving, right? Are they moving in straight lines? No. They're moving on curved trajectories, right? And in fact, some of these move so much they actually follow a closed trajectory, an orbit. And in fact, they all seem to be orbiting around a common spot identified by that star. Okay, so there's something in there. You know, we know what it takes to make an orbit. You have to have a mass, and then something will orbit around the mass, like the Earth orbits around the sun. You can now, you can't, you know, in this image you can't see anything. In fact, with the radio telescope, you can see a radio source sort of at that spot. It's not especially powerful. It's kind of unusual. But is there something there? Well, it turns out you can calculate what the mass of whatever there is by knowing the separation of these stars, the distance of these stars, the size of the orbit, and their speed. And you get all that from these data, right? You can get the size of the orbit and get their speed. They're moving pretty darn fast. And the mass that you get that would be required to make the stars move in that way is, in fact, 4 million solar masses. We have a supermassive black hole in our backyard. Think about that, okay? So there you go. So this is right here in the Milky Way. We have a supermassive black hole. So let's come, someone mentioned Andromeda. So many of you have seen Andromeda. You can see it just with binoculars or even naked eye on a really dark sky. It's a near neighbor. If you could get outside of the Milky Way and look at it, it would look kind of like Andromeda, okay? Flattened distribution of stars and gas. And so people have done a similar kind of thing. Andromeda is 100 times further away than looking at the center of our galaxy, but you can make measurements of how stars are moving in the centers of this galaxy. And again, you can estimate how much mass has to be down there, dark mass that you can't otherwise identify, and it's a lot. It's 100 million times the mass of the sun, 10 to the 8 solar masses. Okay? So we're finding the remnants of these burnout quasars, supermassive black holes, right here in our neighborhood. Okay, a key tool to advancing this research, which I mentioned previously, is the Hubble Space Telescope. So let's talk a little bit about Hubble Space Telescope. Hubble Space Telescope was put into orbit in 1990. Okay, and so what's special about Hubble Space Telescope? Well, it's, you know, fair-sized telescope, but you measure the size of a telescope by the diameter of its mirror, right? How big it is across the mirror, because that tells you how much collecting area it has. This telescope is a 2.4 meter diameter mirror telescope. Okay, well that's kind of big, but by modern standards, that's not an especially big telescope. In fact, Ohio University is partners in an observatory in Arizona, the MDM Observatory. At that observatory, we have 2 telescopes that our faculty and students use for carrying out research. This is one of them, the 2.4 meter telescope at Kitt Peak. It's the same size as the Hubble Space Telescope, okay? But it's on the ground. So you can do good research with this telescope, but you can do amazing things with Hubble. So why is that? I mentioned before that Hubble's ability to get very wonderful images of fine details in the sky. Why is that? If you go out and use a telescope here and you look at stars in the sky, what happens is the image of the star ends up being blurred out by the motion of the atmosphere. Okay, you've got little pockets of air moving around, the light's coming down, and it causes the light rays to bend a little bit. So you've seen this kind of thing if you are sitting at the breakfast table looking across the top of the toaster while the toaster is on and you see this wavy stuff, right? Or look across the hood of your car on a hot day and everything looks kind of wavy. Same thing. You're getting little variations, air currents, variations in the density, which changes from physics terms the index of refraction. So the light rays bend rather than going in a straight line. Okay? So the problem is things, you know, what you would otherwise get as a nice crisp image gets blurred out to this blob if you're looking through the atmosphere. Well, there's places you can go on Earth to get better better atmospheric conditions. So if you're on a mountaintop near a desert like Arizona, or near the ocean like California or Chile or Hawaii, you get better atmospheric properties, sort of laminar flow, which gives you more stability, but it's still not great, right? So this is what astronomers call seeing. It means the blurring of the atmosphere. We don't really tend to have really great seeing here in Ohio, which is why we go to Arizona to do our research. But better than going to Arizona is to go to space, right? You don't have to worry about this atmosphere stuff. You get above all the atmosphere, don't have to worry about that anymore. So that was one of the biggest motivations for launching the Hubble Space Telescope. So now you're above the Earth's atmosphere, and you can now peer into the very inner parts of a galaxy and see what's there. And you can measure the stars in the very inner parts of the galaxy, see how they're moving. Or what I've done in my research with my collaborators is we study gas that is often found in the centers of galaxies. And in many cases, it's in an orbiting disk. And remember what it takes to measure the mass of a black hole. You need to measure speed and the size of the orbit, right? Hubble allows you to measure separations down to very tiny scales because of this ability to see fine details on the sky. So we make measurements of gas rotating in the center parts of the galaxy. And remember, the signature of the gas's motion is a Doppler shift if the gas is moving towards you or away from you. So here's how this looks. Here's the image of the central part of a galaxy. You can see it's darker here. It's a negative image again, right? So the largest concentration of stars is right here. We zoomed in with Hubble. This is actually from the Hubble Space Telescope, central part of the galaxy. And we overlay on this an aperture, what we call a slit, right, which you allow the light to pass through. So you keep all the light that's coming through this red rectangle. You throw everything else away, right? Now, at each point along this slit, you take the light in each little element and you disperse it. You spread it out into a little rainbow. You look at its spectrum, okay? You look at the spectrum at each little point. You get a little spectrum at each point. And in the spectrum, this is what a spectrum of one of those little regions looks like. You get these spectral lines from warm gas sitting there in the inner part of this galaxy. And this is a case, again, this is like a fingerprint of the elements that are doing the emission. This is a hydrogen line. These are nitrogen lines. This is emission from sulfur, right? And we know what the wavelengths are in the lab. We go here, you measure up and down the slit, right? And you can measure the locations of those lines. And you see on one side they're a little bit red-shifted, meaning the gas is moving away. And the other side is a little blue-shifted, meaning it's coming towards you. You get the speed of this rotating disk, right? That's how we measure the speed. You get the separation, you can measure the black hole mass. And we've measured this in multiple galaxies, finding masses of typical numbers in the kind of galaxies we're looking at would be 10 million times the mass of the sun. Pretty garden variety supermassive black hole, if such a thing, if you think of that, those two words go together. Okay, so these supermassive black holes seem to be very common. Now, due to our measurements and measurements by other people, it's clear these are common, even ubiquitous, in galaxies of any significant size. And that says that the formation of a galaxy, the formation of the matter coming together to form stars, the formation of the stars goes hand in hand with forming this very massive compact object, this supermassive black hole in the center. And that happens when the galaxy is young, right? Because we see these quasars looking back in time when those galaxies were younger than they are today. Okay. Yes? What is the lower limit for supermassive black hole? The answer is we don't actually know, because as the mass of the supermassive black hole gets smaller, it becomes more and more difficult to see, right? Because one thing to remember is this black hole is embedded in a galaxy of stars. And if the mass of the black hole is very small, the gravity is all dominated by the stars, it's hard to see the signature of the black hole. Okay? So I want to say just a very few more things about this amazing instrument, the Hubble Space Telescope. Okay? So I said, it's great, can do all these amazing things. It's better than telescopes on the ground. So why don't we do all of our astronomy from space, right? Why do we even have this telescope in Arizona? We should just concentrate on space. So why don't we just give up on astronomy from the ground and only work from space? Why? Expensive. Look at that, right? This was the cost of the Hubble Space Telescope, and factoring on $2.5 billion, right? And then factoring in all the additional cost of operation, and there were 5 repair missions with the space shuttle. Very expensive, $10 billion total, and still going because we're still operating this telescope. Very expensive. So we don't have a large number of these space-based telescopes. But it's amazing what they can do. So why is it so expensive? Well, you have to launch it up to space on this rocket, right? But there's all kinds of technical challenges. There's radiation out there in space, and there's other things that you may not have even thought about. So let's think about you want to change the direction that your telescope is pointed, right? So on the ground, some of you have used small telescopes, right? You've got a telescope, you want to change its orientation. What do? You grab the telescope and you push it over to a different orientation, right? Okay, so when you're doing that, you're grabbing the telescope and basically you're pushing against the ground to move the telescope. Suppose you want to move the Hubble Space Telescope. What do you push against? Right? How would you move it? And once you got it started moving, how would you stop its motion? Right? If you want to point to a different part of the sky. Okay. Any thoughts on that? Yes. Gyroscopes. Gyroscopes. Okay, so do you want to say a little more how that would work?
Yeah, so like 3-axis gimbal gyroscopes using angular momentum, spin them,
Okay, excellent. Okay, give that man a T-shirt. Okay, but that's a pretty fancy answer. So we're going to do a little demo to help you visualize how this works. Okay. So let's suppose here I am out in space, right? And this is a freely rotating platform here, right? So I'm out in space and sort of freely there. Now, if I want to turn, how do I turn, right? If I turn, it's like one part of my body turns and the other part turns the other way, right? So what do I do here? So the answer is you need a reservoir of what physicists call angular momentum. You need an angular momentum reservoir, a reservoir of this spinning motion in a sense, okay? So here's going to be my reservoir of angular momentum. It's basically a flywheel. Okay, so I'm going to spin this up. Try not to injure myself. Okay, so now I'm going to get on this platform. Okay, now suppose I want to turn my orientation. I take angular momentum out of the flywheel until I get to my new location, and then I put angular momentum back into the flywheel where I am right there, right? When I want to move, I break the flywheel and then spin it back up. Okay? So that's how you reorient a telescope in space. But it takes a lot more technology, than doing this on the ground. So, and there's a lot of other factors that make working in space just a lot more challenging, which is why these instruments are so expensive. So, Hubble Space Telescope, who knows this Hubble name? Where does that come from? Astronomer. Who said that? Astronomer. You know his full name? Does anyone know his full name? Edwin Hubble. Okay, here he is. And anyone know what Edwin Hubble did? I mean, he did something kind of important to get a telescope named after him, right? So what did he do? He did observe stars and create catalogs, but there's some other things he did that really made him more famous, right? Yes? He measured that everything's moving away from each other. What does that mean? Expansion of the universe, okay? So you go out, you look at galaxies, and you can measure speeds of those galaxies. We've talked about this. How do you measure speeds of something out in space? With a spectrum, and you measure the redshift or the Doppler shift, right? Tells you about the motion. And there was a curious fact, actually, he wasn't the very first person to start noticing this, that you look at galaxies, and there seem to be many more moving away from us than coming towards us, right? Most of them show a redshift. Almost all the galaxies you see show a redshift. Hubble found something even more significant, that the redshift is correlated with distance. More distant objects are moving away faster. And that is exactly what you expect if you have an expansion of a universe from a single point, right? It's the same as what you would get with any kind of explosion, right? Blow up a bomb, right? Come and look at it a few microseconds later, and the stuff that's furthest from the central explosion is moving the fastest, right? Speed correlates with distance. That's what you have in an expanding universe. So Hubble made that discovery, which had all kinds of important consequences from that. So the Hubble telescope was an amazing piece of technology. It was really very, very closely linked to the Space Shuttle program. And this shows the orbit of the Hubble Space Telescope. It's a very low orbit. Okay, it takes about 90 minutes to go around the Earth. And as I said, it's unusual, and there were actually 5 different repair missions that went up to put in new instruments to replace solar panels and gyroscopes that failed and things like that. It's still working amazingly well at the current time. Okay, we're still getting lots of great data. Now, something really interesting is going to happen in a year and a half, 2018, in terms of astronomy from space. And that is that Hubble's going to get a companion. Who knows what that is? A very important companion. Okay, so yes. The James Webb Telescope. All right, give that person, do we have any more t-shirts? Give that person a t-shirt. Okay. Okay, so this is an image of the James Webb Space Telescope. Remember, Hubble Space Telescope, 2.4 meter diameter, right? 6.5 meter diameter. A lot bigger. Okay? Pretty expensive. Right? Almost got canceled several times, $8.7 billion. But it will do even more amazing things. Now, some people talk about the Webb telescope, some people call it the JWST, as being sort of the replacement for Hubble. That's not really accurate, because the kind of measurements that this telescope will do are quite different from Hubble. In particular, this telescope is optimized for infrared measurements. Okay, infrared measurements allow us to see these objects where the light has been highly redshifted because they're exceedingly distant. It also allows us to, more close by, to peer into regions of obscure, dusty environments where the very youngest stars and planets are forming. Okay, and the dust would block visible light, but the infrared light gets through. So it really is going to be complementary to Hubble in terms of its scientific capabilities, but it's an enormous jump over what we've had before. So this looks kind of bizarre, right? There's several interesting features. First of all, you see these hexagon panels, right? With that kind of diameter, you can't just put it in a rocket fairing and send it up. It's got to be folded up. That's a segmented mirror. The telescope's going to be kind of folded up, and it goes out there in space, is going to unfold. Okay? So that's a pretty big technical challenge. Then there's this whole thing here. If you're working at infrared wavelengths, anything that is warm is glowing. Okay? So you got to get away from anything that's warm, and you got to keep this telescope cold. They're going to keep it about 50 degrees Kelvin. Okay, so pretty cold. And you can put things like liquid nitrogen, liquid helium or something, but eventually that boils off and runs out after just a couple years. So this uses a passive cooling system. And this thing here is a very sophisticated sunshade, because the biggest source of heat is going to be light from the sun and actually from the Earth and moon. So this sunshade is about the size of a tennis court. Okay, so that's another thing that you've got to fold it all up to fit it into the rocket fairing, and once it gets out there in space, it's got to open up, and hopefully it all works because we don't have a space shuttle to go up and fix anything anymore, right? So so James Webb Space Telescope, who was James Webb?
Director of NASA during the Hidden Figures epoch.
Yes, in fact, he appears in Hidden Figures, right? So James Webb, Hubble was a scientist. Most of these telescopes are named after scientists. And James Webb actually was a lawyer. But he was a pretty effective administrator because he was running NASA during this critical phase of the mid-1960s when we were gearing up to the Apollo program and eventually landing a human on the moon. And so he was the second NASA administrator during this critical phase, and NASA decided to name it after him, which is a little unusual. These are usually named after scientists. So there's one more thing about the Webb telescope that is worth mentioning. So you saw that the Hubble is in this low Earth orbit, right? And that was great because there were problems with Hubble. The space shuttle could go up, astronauts could fix it. They did it multiple times. To get away from heat sources, to get away from the Earth in particular, the JWST is going to be in a much more distant location. And so in this cartoon, this is the sun, right? This is the Earth. Earth's going around the sun. And these little green points are what are called the Lagrange points, okay? They're points of gravitational equilibrium, sort of quasi-stable, where you can locate an object there and have it persist in a stable orbit. So this will be at what's called the L2, the second Lagrange point, is where we're going to put the JWST. And remember, the Hubble was at, 500 some kilometers? Yeah, 559 kilometers from Earth. And this is at 1.5 million kilometers. In fact, it's not even orbiting the Earth. It's in a solar orbit. But because it's at the Lagrange point, it preserves its orientation to the sun and the Earth. And that helps it. You can keep the sunshade on this side, and you're always obstructing the Earth and the sun, okay? And keep it cool. But it better work the first time all that stuff, sunshade, mirror, all that stuff unfolds. Cross your fingers, $8.7 billion. We hope it works, because if it doesn't work, there's not going to be humans going out to fix it. Maybe robots, but yeah. So when this October 2018 is the launch, not that far away. We've been waiting a long time. So mark your calendars. It's going to be a big day when this goes up. Okay, so that's all I had to say, but I'm happy to answer any questions. Yes?
Joe, you mentioned the galaxies almost ubiquitously have black holes. I'm thinking of the chicken and the egg. Which comes first, the galaxy or the black hole?
Yeah, good question. So which comes first? If galaxies all have black holes, where we think of a galaxy as stars and gas and dark matter held together by gravity, does that all come together first and then the black hole forms, or vice versa, right? And that is an excellent question, much debated, and I don't think fully answered, but I think there's indicators that it's sort of symbiotic at some level. Because, for example, the black hole, if it starts accreting and turns on this quasar, can put out so much radiation and those jets squirting out and everything, they can actually push a lot of the gas out of the galaxy and shut down the star formation, right? And so that's called feedback, right? So the gas collapses to come together in the first place, starts forming stars, then you build up the black hole shuts it down. There's actually scenarios that sort of work in reverse, right? Where you actually bring in matter and that helps build up the black hole. So, but I think the case that these are so ubiquitous means that they sort of go hand in hand, right? And when you see a quasar, that's a growing black hole, right? So you start, it's a very active question is, what do you start with? What do you start with, like a star cluster that collapses to with maybe 10,000 times the mass of the sun that builds up. We don't really know that. That's a really interesting question, is how does this whole thing get started? Yep. Yes? Go ahead.
I was just wondering, I mean, when you identify a black hole for the first time, would you identify it by the mass or the emission spectra? Because I'm wondering if you have other bodies with very similar emission spectra. Is there a signature emission spectra?
Okay, so you want to find black holes. Do you find it just by the motion, right? Or do you find it from those emission signatures? And the answer is both of those are ways to find black holes, and they're in different states. If it has all the emission, that means it's a growing black hole, with fuel going in, right? And if it's quiescent with none of that going on, the only way you're going to find it is through the things orbiting around it. In either case, that's how you can find it. Now, the emission spectrum for these quasars is actually very unique. The specific pattern of lines, and the lines are actually very broad, having to do with the Doppler motion of gas swirling around the black hole. So they have a very characteristic signature when you look at it. Yep. Scott. Does the mass of the black holes change over time? And the answer is yes, because when you see a quasar, you are seeing a growing black hole. It is gaining mass because mass is going into it at that time. Does it ever lose mass? The only way black holes can lose mass is through Hawking radiation. Some of you know about that. It's a quantum mechanical phenomenon, and the rate at which they lose mass, especially for these supermassive ones, is minuscule, right? Over the entire age of the universe, the impact on the mass is negligible, okay? Yes?
So now that we know where these quasars are, we know where supermassive black holes are, and we also know different stars that are orbiting around those. Are there any studies going on right now to see if the gravitational effects of stars near those black holes have altered spectra, emission spectra?
Okay, so, yep. So you look at these stars close down to one of these black holes. Are they unusual in some sense in terms of their spectra or something, right? I guess because they're being influenced by their environment or the black hole. The only the place we can look at that best is in the center of the Milky Way, where you can actually resolve individual stars, right? When you look out these other galaxies, you're seeing ensembles, collections of stars. So the stars in the center of the Milky Way, it is a very unusual population of stars, okay? Now, it's not clear that the black hole really has anything to do with that or not. There's other things that are kind of unusual in that environment, but there's an unusual population of the stars are very massive, right, and have some unusual characteristics. We don't really know why. Okay. Yes?
I was just going to ask, so if the black hole's growing and we're seeing it like years and years after, what's like the time frame that you can see a black hole like growing on, I guess? Like, if we're looking at one now, will we be able to see like a couple years from now, or like a long time from now, will somebody else be able to tell us?
Yeah, so when this black hole is growing, how long does that persist, right? Are we going to, if you go observe it tonight and it's there and you come back in a year, is it still on, or will it have winked out, right? And so the answer is that, first of all, these quasars do vary in their brightness, right? The fueling is varying because you'll see them go up and down in brightness. That's another way that these have been discovered, is they're not constant sources. There are a few cases where these have faded on a human lifespan. They've faded enough that they've almost disappeared. These are sort of closer by, not as powerful, what we call an active galactic nucleus. They fade significantly, like a factor of 30 in their brightness or something like that. It's not real common. You can calculate through a variety of means the lifetime it would take, sort of the average lifetime of this quasar episode, the fueling episode, and average lifetime is about 10 million years. Okay, so on a human time scale, that fueling, it may go up and down, but it's a long time. So.
How does the supermassive black hole at the center of the galaxies, does that relate in any way to the shape of the galaxies? Like, is the spiral shape of a lot of the galaxies that we see basically a fossil of the accretion disk?
Yeah, so there's an indication that the strongest connection is between black hole and the round part of the galaxy, right? So this is a galaxy kind of like the Milky Way seen edge on, and there's this bulge in the middle, right? And this is a galaxy that's all bulge, it's all round. And in fact, earlier on, people were saying there's a very tight correlation between the mass of the supermassive black hole and the mass of the round part of the galaxy, the bulge, right? There seemed to be in fact, you know, when I was speaking on this 5 years ago, I was saying, oh, there's this amazing correlation, and that relates to how they form and all that kind of stuff. That's kind of broken down because it has to do with what astronomers call selection effects. It's a bias in the samples that were being used. As we've broken out to study different kinds of galaxies, we find these black holes and the correlation breaks down. But I think there's still some indication that the biggest black holes live in the galaxies with the really big round parts to them.
Thank you.
Okay.
Thank you. I really appreciate it. It was a great talk. Absolutely great. I'm sure Dr. Shields will hang around and answer questions for some of you, but I would really like for you guys to thank Dr. Shields again. It was a great presentation.